All right, hello. Today I'm Connor Jellum, and as I am every day. And today we are actually going to be making two types of Play-Doh, conductive and non-conductive Play-Doh. But we're going to start with conductive Play-Doh, and just to kind of explain the science behind both of these, or the chemistry really. There's like different kinds of like mixtures and solutions, and there's differences between them, even though it doesn't sound like it. A lot of times those words are used synonymously, but there actually is a difference, and here it is. So salt and flour, when they're put together, let's just say, they actually produce what is called a mixture. And what that means from a chemistry standpoint is that these two things, salt and flour, can actually be separated. They're put together and they're mixed. It's very hard to separate them, but if you got like certain tools, you could separate them. They can be separated. Now, when you add like water and apple juice, for example, or water and food coloring, those things cannot be removed, and that's called a solution. Those things cannot be separated after they're put together. It's nearly impossible. They're mixed completely together, unlike the mixture of the salt and flour, which can be like sifted to be separated. Now, for Play-Doh specifically, both conductive and non-conductive, when you put them together, chemical reactions take place, and that makes it so that it's actually essentially a solution. They can't really be separated after they're put together. That's why when you see Play-Doh, you don't see little bits of salt or little bits, well, actually maybe salt, but you don't see little bits of other things in the Play-Doh. It looks like a solid thing. And that's because when you put the water and the flour and the different ingredients, it actually creates trying to think of the word. It causes them to stick together, basically, and they can't really be taken apart. Especially after it dries out and becomes like the Play-Doh that we know that's in cans and stuff. It can't really be separated. You can't take the different parts and ingredients of the Play-Doh out of each other. But to get started, we're going to get 1 cup of water and 1 cup of flour. So, 1 second. All right, sounds good. Here's a cup. So we're going to get 1 cup of water, 1 cup of flour, 1/4 cup of salt, 9 tablespoons of lemon juice. So basically, everything we need. In a medium-sized non-stick saucepan. So I'm gonna have to grab a saucepan real quick. Okay, so now what we have here is our saucepan and our cup. So we're gonna start with the water. So 1 cup of water. Right about there. All right, and that's gonna go in to the saucepan. Awesome. So then we need 1 cup of flour. I'm actually gonna grab something to scoop it out real quick. This is 3/4 cups. Put it in there. There we go. Just measure that out in here. And it's about a cup. Pour that on in with the water. Awesome. So we need 1/4 cup of salt. There's a decent bit of salt. I'm going to use this one for that. Seems a little bit big, and we only have pink Himalayan salt, unfortunately. This should work. You need a lot of salt for Play-Doh. Even it out. Alrighty. Awesome. We got the salt, the water, and the flour. And now we need 9 tablespoons of lemon juice. Here's 1 tablespoon. We're gonna have to do this 9 times. It smells very acidic. That's 1. That's 2. 3. 4, 5, 6, 7, 8. And I spilled some in there, so we're gonna stick with 8 for now. Because I spilled a little bit, probably about a tablespoon total. Okay, I need 1 tablespoon of vegetable oil right here. Only 1 tablespoon. Lemon juice far outweighs the vegetable oil, it seems. There's 1. And then we need, food coloring. Okay. Gotta be careful with this, otherwise I'll turn blue. Awesome. Oh, got it on my hands. Okay, so now we're gonna mix it up a bit. Then we're gonna put it on medium heat for a little while. And mix it up for a little bit. Okay, so we're gonna stir it continuously for a little while until this mixture thickens up. Looks like I got some bacon there. It's got a little bit clumpy, but it's just heating up now, so that flour should kind of dissolve into the rest of the mixture. And I'm just gonna keep stirring it until it starts to thicken. Okay, as you can see now, it is more dissolved. The flour isn't as clumpy as it was, but it's definitely not thick yet. And that's what we're trying to get, is that thicker consistency. So it's gonna take a little bit more time. Okay, as you can see, it's much thicker now. I'm gonna take a little bit more time to get it fully mixed, but it's definitely looking more like Play-Doh, way stickier. And yeah, it's been about 6 to 7 minutes at this point. Okay, so we got the Play-Doh. It's obviously thickened. It's more of a Play-Doh mixture, and we're just gonna like knead it into this flour that I put on the tabletop so that it stops sticking. And this is the conductive Play-Doh, and I'll explain the difference a little bit more in depth later when I make the non-conductive Play-Doh. But the main difference in ingredients is the salt versus sugar. So in the non-conductive, there's going to be sugar instead of salt. And you'll see that when I make the non-conductive Play-Doh. But this is the conductive Play-Doh, and yeah, this is about the final product. So obviously the flour is going to get mixed in a little bit more, but yeah, this is about what we got here. So thank you for watching how to make conductive Play-Doh. Okay, so now what we're making is non-conductive Play-Doh, and the science behind how this Play-Doh is made and how it works is basically the same. However, what happens, where the difference comes in, is we're not using lemon juice and we're not using salt, which are two ingredients that are very conductive. And when you mix those with the Play-Doh, it makes it conductive. Now, when you use sugar, which is kind of what we're using to replace the lemon juice and salt, maybe not replace, but that's the different ingredient. When you use sugar, it actually doesn't hold the proteins together as well. And because of that, and because of just other chemical situations that go on, chemical reactions, it doesn't actually act as a conductor, but actually acts as a insulator, the exact opposite of a conductor, which is very interesting. But yeah, so we're gonna get started. So we need 1 cup of flour. So grab that. Okay, there's a cup of flour. And then we need 1/2 cup of sugar. That's all too much. A little more than that. Alright, so there's our sugar. And it's a decent bit of sugar. Then we need 3 tablespoons of vegetable oil. And we're actually not going to add the water yet. What we're going to do is add the vegetable oil, then we're going to stir it until the vegetable oil is not really there anymore. It's mixed in completely. So there we go with the vegetable oil. Now we're going to start mixing. This might take a little bit of time. We actually don't heat it up like we did before though, which is interesting. Okay, so we've got the Play-Doh right here. It's honestly a little bit disgusting looking. But that is it. It looks almost exactly like the other one, but it's sugar instead. I actually had to add a little bit of extra flour to make it the right consistency. I'm adding more now, but it was a little too watery. But yeah, that is it. And we're going to be using this Play-Doh later. All I have to do now is really knead it. I can do that right while I'm talking. But really, like, we're just going to be saving this for later. We're going to be using it in some more experiments, the conductive and non-conductive Play-Doh. That's why they're different colors. The last one was blue. But yeah, that is it for this video here. Just got to knead it out, knead some flour into it, and that's going to be all that's left. So yeah. Thank you for watching this. Okay, so what we are doing now is using the conductive and non-conductive Play-Doh that we made yesterday. And we are gonna be experimenting with LED lights. I have cactus-shaped ones. Yeah, we're just gonna be experimenting with LED lights. And in this specific instance, we're gonna be using what's called a series circuit. And what a series circuit means is basically every single, the current can only actually go through one pathway. So it's only going in one direction all the way around. Because it's still a circuit, but it's a series. So it hits each one in a certain order, like a series. And that might be hard for us to tell because light is very, very fast. But it would all go like boom, 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 boom. You know, it would hit each one in a consecutive order, in a consecutive series. And actually, we're going to be using LED lights, which I think a lot of us don't know a lot about. But LED lights, how they work is the light, the current will go through, we'll start at the beginning and rush through to the end immediately. So it'll go straight, from here, the battery pack, to here and all the way through. Because it's not in a circle. LED lights tend to be strands and they'll go all the way through, but like all the way across. But in this case, they're going to be going in a circuit because we're going to connect them to make it do that. And yeah, so let's get started with that. Okay, so what I've been trying to do is figuring out how to get the circuit to work. And unfortunately, I do have my LED right there. But it is not turning on despite the Play-Doh. So I must have done something wrong. I've checked several times to see what I could have been potentially doing wrong, and I don't see any flaws. That's just another LED that I didn't cut off. But I've looked over it multiple times and couldn't figure out exactly what was going on. So what I'm going to try to do instead is just explain what should be happening. Given the type of Play-Doh we have and the battery packs we have. So essentially what I've done is intertwined from this battery pack all the way over, to this battery pack over here. The cords here are pretty long, but these are all different battery packs intertwined right here. And what should happen is this battery pack and these battery packs should be making a circuit, and since the Play-Doh conducts electricity, because it's the salty Play-Doh, this light should be turning on. In theory, the light should be turning on, despite the fact that this is not connected to these whatsoever. It's been completely cut off. Now, that's what would be happening when the Play-Doh was in this circuit, in this instance, if the Play-Doh is a conductor. Now in this situation, as you can see, I added a ball of Play-Doh right here and connected another LED light, which happens to have a cactus on it, which is pretty cool. Still a light though. And we're still using conducting Play-Doh. So basically this is just an extension of what happened in the previous example. The lights are all still connected to the battery packs, and since this is a circuit, the battery would start on the positive, or the energy would start on the positive side and flow through all the way through here and in a circuit and out. And it would keep doing that because the batteries keep producing that energy. When you use a battery, you have an energy that is getting pushed farther and farther. And actually what would happen since there's multiple battery packs, is it would start over here, I believe, or where the current started. It would start, it would go through, and then it would hit the other batteries, so more energy, and would actually stack on itself, and in theory get stronger and brighter, because those particles would start to be emitted through the lights, those particles of energy that the batteries are giving off. And it would actually make them brighter because there's more batteries and more energy. So that is what is going on with this specific example. Yet again, similar situation. So again, similar example, just another longer circuit. Now, light is emitted, and there's an amount of energy emitted with light, obviously. And it would probably not be easy for us to tell as humans, just because light is very fast, very hard for us to really measure without proper instruments. But since there's so many lights now, there's 3 lights that are, well, in this situation 4, but since there's 3 lights that are being used, it would actually take more energy from the batteries, so the brightness wouldn't be as intense with the 3 as it was with the 2 or the 1. And now again, just to draw attention to potential errors, so one side of these LED lights is positive, one is negative. The positive side has to be receiving the light, the negative side has to be giving it out. So all these have to be faced in the positive way. Now, I've tried every single combination, and unfortunately they're not working in this instance for whatever reason. But in theory, if they're all facing the same direction, all the LED lights, then you should be fine. And the light should be traveling through all of them. So that is this example. Okay, so now for this example, what's happened is we have the energy running through from the battery packs yet again, but I've removed an LED right here. That LED used to be connected to these 2 Play-Doh balls. And so what would actually happen is it would travel through, and it would actually be broken. So the circuit's completely broken, and I have an example of that right here. So the circuit's broken, as you can see right there. And when that happens, the energy just kind of stops. It's almost as if there was a switch. But the light wouldn't be able to work with all of the LEDs. What would be happening is it would be traveling up and potentially going through here and here, causing energy to work, but it wouldn't be going in a full circuit, so the energy would just be emitted right there. And so that's what would be occurring in this instance. When we take out that 1 LED, it wouldn't be traveling in a full circuit because there's a break right there. It's almost as if a bridge was lit up. And that's kind of the idea behind switches actually as well, is when a switch is turned off, it's almost like the cars on a bridge would have to stop if the bridge went up. And that's the same with the switch. The energy going through, the particles traveling through the circuit would have to stop and sit there like a car would on a bridge, because they couldn't travel through anymore. So yeah, that is this. Okay, so what's going on here is we now have red Play-Doh, as you can see, which is actually the non-conductive Play-Doh that we made, which means it wouldn't act as a conductor, it would act as a resistor. And what that means is that it would not allow the light to actually receive any energy no matter what. So in this instance, I couldn't get the lights to work with the regular Play-Doh either. But this is actually what should be happening, because the red Play-Doh, the non-conductive Play-Doh, acts as an insulator almost. So, and that's because of the sugar that's in it rather than the salt and lemon juice. And so when the current starts going through here, it's going to connect all the way through here, but then stop. It's not going to be allowed to get to the light on either side, because it's acting as an insulator and stopping the electricity where it stands. Now, this is going to be the case for all of them going forward. So if I just put this right here, if I do that and grab a little bit of Play-Doh, and then take this and stick it in here, and then we're going to grab another set of our LEDs. Sorry, my dog's in the background. Then the lights still won't work despite situation, same exact thing. The Play-Doh is an insulator, so it wouldn't allow the currents to flow through it. And that's just going to be the case for all of them. We could even just, if I place this right here, we could even just take this and this, still connected, and then get a little bit more Play-Doh. This Play-Doh is a lot stickier because of the sugar, I believe. And put it right there. Probably makes it a better insulator too, that it's sticky. And then place these in here. Then it's just gonna be acting the same exact way. It's going to be an insulator. It's not gonna allow that current to travel through, and removing that LED right there with the cactus on it isn't gonna make a difference because the lights aren't gonna work anyways. Or they're gonna work very little. Now in this case, they're just not working at all no matter what. But this is a proper example of what non-conductory Play-Doh would be doing to the lights. Okay, so what I'm going to be showing everyone now is what we call parallel circuits, and they're similar to series circuits, but they have multiple branches, and what that means is that the energy is the same. You're still getting the same amount of energy flowing through all the lights, but since there's multiple branches for the light to travel through, or the energy to travel through, that means that the lights are going to have an equal amount of energy is going to be flowing through, but the lights are not going to be getting the same amount of energy because they are on the same, they're all getting the, well, here, I'll explain it as we go along with more examples right here. So what we're going to do is put some conductive Play-Doh right here, and get some conductive Play-Doh right here. And now when we grab the LED, and again, unfortunately, it's not actually working, but this LED would be very bright because all of the energy is going into that one LED, these branches are receiving it, and the LED is getting all the energy. So there's one branch. Now when we get another LED, let me put that right here, in theory, they would both be lighting up because they're both getting the energy, but now that there's multiple branches, each one might be a little bit dimmer than it would be if it was just one. Now, what we were doing before was we would have one lined up here, and then just one LED here, and it would connect to some Play-Doh up here, and then this LED would be connecting to that same Play-Doh. So there would be only one branch going into each conductor, which is the Play-Doh. But in this situation, both are connected to the same ball of Play-Doh, and therefore they're going to be getting the same amount of energy as all of them be going through. All of them, if it was just one, would be getting. But since they're both connected, their sum is equal, but the amount of energy each one has is less. So then, similarly, if we just add another one right here, if the lighting was working, they would all dim a little bit because now 3 are getting the same amount of energy as 1 was getting before. So the sum is the same, but the amount of light that each one is actually getting and emitting is actually less because they're all getting the same amount of light as just one would be getting. So that is what would be happening with a parallel circuit rather than a series circuit. Okay, now just a quick explanation of the non-conducting Play-Doh in this situation. Same as I was saying before, we have non-conducting Play-Doh made of sugar here, and this is actually what it should look like because the Play-Doh is actually suppressing the energy and not allowing it to reach the lights. So same situation as before, it shouldn't be allowing the lights to work, or it should be allowing them to work very, very little. But despite that, the circuit being parallel or a series circuit doesn't really matter. It should be suppressing it. It should be acting as an insulator when we have this Play-Doh here rather than this Play-Doh right here. So yeah, that is the explanation of the non-conducting Play-Doh in a parallel circuit. It's about the same. So yeah. Okay, so now what we've got here is actually a mixture of the series circuit and the parallel circuit. So what's happening here is, as you can see, it actually works as a circuit, going all the way around like a circuit, starting battery pack here, going around a circuit. Well, series circuit, my apologies. So it's acting as a series circuit, but then you also see how this one's connected to multiple, because this one's in the middle, it's connected to this one, which is connected to this one and this one. So it's acting as a mixture of a series circuit and a parallel circuit, because there's that connection right here that's not normally there. Because as you remember from the series circuit, it went all the way around, and this one would be connected to another set of Play-Doh, and it's just a complete circle. But because this goes through the middle, it is partially a circuit, but it also acts as a, or it is partially a series, but it actually also acts as a parallel circuit, because this one is connected to this one, which is connected to the two others. So because all three are connected to this one, they're going to have a little bit less energy than just a classic series circuit. This is going to, now, again, it's not really working too well, so these lights aren't actually on. In theory, they would be. They'd probably be a little bit more dull than the series circuit would be, because this is also partially a parallel circuit. But if we were using the red Play-Doh, the non-conductive, they wouldn't be working at all. There's no way, or they'd be very, very dull. So yeah, that is the series and parallel circuits combined.